Welcome back, nerds, to the exciting conclusion of graphing rational functions. We will finally finish this lesson today. We just have 3 more questions and call it a day. Call it quits on this material. I tried to start this question on Friday, but I realized that I would have been rushing through it, so I stopped. So first thing I would have done, which I did do in the last video, was write it as a stacked fraction. I only typed them sideways for space purposes, just so I had more space to, do work. What we have here is a rational function that for the first time has the degree of the numerator higher than the degree of the denominator. Some math teachers get cutesy with it and they say that this is a top-heavy function, whereas the one that we did on Friday, this one, we would have said was bottom heavy because the degree on the bottom was bigger. I don't know. Some teachers say that. It's up to you if you want to use that kind of terminology. Here's what I know. If the degree of the numerator is larger than the degree of the denominator, my end behavior asymptote is not horizontal. This is what I know. So how do we find said end behavior asymptote in a situation like this? When the degree of the numerator is higher, the way you find your end behavior asymptote is through long division. We're going to do polynomial long division to get an end behavior asymptote. Don't write too large. You don't want to be pinched for space. Yes, because the numerator has a larger degree, I'm going to have to use long division to figure out what that end behavior asymptote is. Also, you can't put something like this into standard form because multiplying by an x is not a transformation. So those whole standard form things are only for the reciprocal functions, which at worst are linear over linear. Okay? So the moment you have anything that's not linear in your question, you can no longer get it into standard form. So this long division is just to figure out what the end behavior asymptote is. Whereas before we were doing long division to get it into its standard form. Okay, watch out. This has a missing term. It's missing its x term. So you got to call it x squared plus 0x plus 1. Oh, crap. Minus 1. Sorry. Minus 1, not plus 1. So remember, when you're doing long division, what you're trying to do is you're trying to make this front term look like this front term. So first of all, what are we going to have to multiply this x by to get an x squared? An x, yeah. But what are we going to have to multiply this 2 by to get a 1? 1/2, there it is. So we've got this 1/2 x as part of our end behavior asymptote. So our end behavior asymptote will be linear, y equals mx plus b. You take this 1/2 x and you distribute it to the 2x and the minus 4. 1/2 times 2 is 1. X times x is x squared. They match like we needed them to. 1/2 times negative 4 is negative 2. Oh, and there's an x. There it is. So we are subtracting straight down. And remember, minus negative means plus. So yeah, x squared minus x squared is 0. That's what we needed. That means that the 1/2 x was right. 0 minus negative 2 is plus. So we now have a plus 2x down here. Bring down the minus 1. Oh, I didn't need to say plus. We have a positive 2x is what I meant to say. What are we going to multiply this 2x by to get this 2x? Somebody said it. Positive 1. And it's going to get me 2x minus 4. You're subtracting straight down. And remember, minus negative means add. So you have negative 1 plus 4, which gets us a remainder of 3. So we know that it would have been written like this when we were doing our polynomial long division, plus 3 over the divisor 2x minus 4. So we are talking about the end behavior of this graph. That means we're talking about what this graph is acting like. What are its y values doing when the x values are really, really, really big? And I would like you to realize that that includes the in-behavior asymptote. So as the x values get really, 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 really big, that remainder will become 3 over really, 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 really big. And 3 over really, really, really big is going to approach what? The bigger the bottom of this fraction becomes, the value of this fraction gets closer and closer to what? 0. Somebody said it. It approaches 0. Imagine 3 over 10 quadrillion. Darn near 0, isn't it? And you could also think of it as this remainder is bottom heavy. And all bottom heavy functions go to 0 as x gets bigger and bigger and bigger. What that means is every time you do the long division, your remainder, I don't know if you've ever noticed this before, but every time you've done long division, as long as you did it right, the remainder was bottom heavy every single time. And that's because you need the degree of the numerator to be less than the degree of the denominator to know that you're finished doing the division. That was always the result. You were done doing division when this thing down here had a smaller degree than what you were dividing by. That means your remainders are always bottom heavy, and all bottom heavy functions tend towards 0. So even though we had a remainder, this thing will always head towards 0. Always. That means for your in-behavior asymptotes, you never even need to figure out what the remainder is, because the remainder will always head to 0 as x gets bigger. So our in-behavior asymptote is the line y equals 1/2 x plus 1. Y equals mx plus b. And we can graph that if you remember your Algebra 1. This in-behavior asymptote is a y-intercept of positive 1 and a slope of up 1, right 2. Or down 1, left 2. No, it's 1/2 x plus 1. Because the remainder, as x gets really, really, really big, imagine 3 over gigantic number. 3 divided by 10 bajillion is essentially what value? Well, if you put it on a calculator, if you do 3 divided by 10 million, what are you going to see on the screen? Stop telling her answer. She doesn't understand why you're telling her the answer is 0. That's useless. Here you go. You ready? I'll use a graphic calculator so you can see several results, okay? Here's what I'm going to do. I'm going to let x get bigger and bigger over and over and over again, okay? You ready? 3 divided by 1, 3 divided by 10, 3 divided by 100, 3 divided by 1,000, 3 divided by 1,000,000, 3 divided by incredibly small. That has 16 zeros between the decimal point and the 3 at the end. So the larger x gets, the smaller this fraction's value becomes. So we're saying as x gets really big, which is the definition of what an in-behavior asymptote is. We're only talking about what's happening way out here and way out here. This fractional value will head to 0, whereas the rest of it will end up being half of what you plugged in plus 1. Okay? Cool. Now connect these dots to the best of your ability. I'm just going to turn the paper sideways because I do better when it's like that. There. We have our in-behavior asymptote. To find the rest of the information about this function, though, we're going to need to factor everything that factors. What I see on the top is a special case. A squared minus b squared. It factors to a plus b times a minus b, so x plus 1 times x minus 1. And on the bottom, I see a GCF of 2. So nothing cancels. That means this graph does not have any holes in it, which we call deleted points. We also call them removable discontinuities. This one doesn't have any. It does, though, have a number I'm not allowed to plug in for x because it would make me divide by 0. And what is that number? X equals 2. That means my vertical asymptote is x equals 2. All right. Would be nice to have some coordinates, right? We could just start guessing and checking and plugging x values in and connecting the dots. But some important things to know are asymptotes, intercepts. Some important things to know are intercepts. Let's track down our y-intercept. I like finding the y-intercept first because it's always really easy. When you're on the y-axis, x equals 0. So all you have to do is let x equal 0 and see what's left over. It looks to me like I'll have -1 over -4, which is positive 1/4. This function crosses the y-axis at positive 1/4. If you make your dot fat enough, no one will be able to argue with you that that is what positive 1/4. X-intercepts. So like the y-intercept, when you're on the x-axis, something equals 0. When you're on the x-axis, y equals 0. But y equals my fraction. So in order to find the x-intercept, you're actually saying, where does the fraction equal 0? And what's the only way that a fraction can equal 0? If the top or numerator is 0. We never let the denominator equal 0 because that would make it undefined. But if the top is 0, 0 divided by 5 is 0. So we're going to figure out what makes our top of our fraction equal 0. And I see two numbers for x that will make that happen. Positive 1 and -1. This graph crosses the x-axis twice. We have to go through those 3 dots and get infinitely close to the green line and infinitely close to the red line. That's going to force a shape that looks like this. And now we just need to know where we are when we're to the right of that red line. Am I above the green dotted line or below the green dotted line? Don't make assumptions, test. So you're going to grab a number and you're going to plug it in. So I like to use numbers that are directly next to the asymptote. That way I'm not having to deal with giant numbers in my fractions and things like that. So I'm going to plug in x equals 3 and see what kind of y value that I get. So we're going to plug in or test x equals 3. And it doesn't matter if you do it here in the factored or in the non-factored form or here in the factored form. It really doesn't matter. I already have it factored here, so I'll just go ahead and do that since I can see that on the screen right now. So we got 3 plus 1, which is going to be 4, times 3 minus 1, which is 2. So 4 times 2, I have an 8 on top. 3 minus 1, or 3 minus 2 is 1. Oh, I have a y value of 4. A nice, pretty coordinate. At least I'm not going to have to plot a fraction. So it's 3 comma 4. That is here. So, I'm sorry? Is the top 6 and not 4? Or not 8, I mean? This number's 4, and this number's 2. Boy, I had me doubt myself. There, knowing that dot is there is enough for you to know that you're in the top zone. You have to get infinitely close to the red line and infinitely close to the green line. Try to go through that dot to the best of your ability. So it looks something like this. Whee! There you go. Ta-da! Thoughts on that? Questions on that? Anything I can help you with? Why I did, couldn't you haves, why didn't yous? Any of that? What ifs? None of that? Okay. Now, it's not going to happen in our notes, but I do want you to know that it is a possibility. You could have a slant asymptote, also, which is what this is, also known as an oblique asymptote, with multiple vertical asymptotes. It didn't happen in the notes, and I can't remember if it's in the homework or not, but yes, it's 100% possible. Okay? You never know. That would make a good extra credit question on a test. Since it wasn't in the notes, but you do have the abilities to do it, you know, maybe like graphing one that's got two vertical asymptotes with a slant asymptote. I don't know. I'm just saying things that you now have the ability to do, but I haven't showed you that. Cool? Now, we get to talk about deleted points. A deleted point is also known as a hole in the graph, is also known as a removable, because we literally took it out of the graph, removable discontinuity. A discontinuity is a number that would have made us divide by 0. But if it's a removable discontinuity, it's not an asymptote. It's just a hole in the graph. This question doesn't even have you graphing. This question just says, hey, what are the coordinates of the deleted point? Where is the hole in the graph? What is the x comma y of that hole in the graph? Okay? So how do we do that? Well, first, we factor everything so we can literally see what values for x are not allowed. Because a hole in the graph is always an x value that's not allowed. That's why it's a hole in the graph. For the numerator, we're looking for two numbers that multiply to negative 12 that add to 1. That's going to be 4 and negative 3. For the denominator, I'm looking for two numbers that multiply to a negative 6 and add to a negative 1. That's 2 and negative 3. Now, if you recall back to the lesson of actually where we started the chapter, when we were multiplying and dividing rational expressions. Anytime you have a factor that's on the top and the bottom, they cancel each other out. So what we know is that this graph, well, this function simplifies to x plus 4 over x plus 2. But we all know, we are all well aware that the original function has two numbers that you cannot use for x. One of them is negative 2, and this graph still shows me that. This graph has a vertical asymptote at x equals negative 2. What this no longer shows me is that this x equaling 3 was an issue. So what we did in the first lesson was we did this. We said, well, it's going to look exactly like this rational function. Oh, but you can't use x equals 3. That means there's a hole in our graph at the value x equals 3. But it's a single coordinate. That means it also has a y value. And in this question, what we're deciding is what is the y value at this x value. And when you have an x, how do you typically get a y? You just plug it in, right? You know you can't plug 3 into this. It's going to make you divide by 0. But you know where you could plug in x equals 3? There. This is literally why we have to write it. Because if we didn't write it, everybody would think you're allowed to use x equals 3. You're not allowed to. But if we plug in x equals 3 to this function right here in the simplified version, it's going to show us what y wanted to be at x equals 3. So we'll do it like this. Because we're not actually allowed to find f of 3. But what we'll do is we'll plug 3 into this simplified version of f of x. And whatever y value we get, that is the y value at this deleted point, at this removable discontinuity. It's a hole in the graph. So we're going to drop 3 in right here. It gives me 3 plus 4 over 3 plus 2. That's 7 over 5. The graph of this function has a hole in it. Literally just something missing. And that hole occurs at the coordinates 3, 7 over 5. And I can prove it to you. So we should have a vertical asymptote at -2, x equals -2, and the graph should have a hole in it at x equals 3. Now this calculator, since it's coloring in pixels, can't show you a hole in it at x equals 3. But if I go to the table, I can see that there is a problem at x equals 3. It says error, right? Now I'm telling you, though, that it cleans up to x plus 4 over x plus 2. And now it's going to trace a red line over my blue line. The colors don't really come out very well, but I hope you can see that they are changing. And you can see that they are the same graph, right? But if I go back to the table, you can see when the original one had a problem, the second one had a value of 7 over 5. There it is. Pretty cool, huh? So that's how you find the coordinates of your deleted point. Simplify, figure out the x you were never allowed to use, plug it into the simplified version, and that will tell you where the y value would have been if it was allowed to exist. Of course it's going to be on the test. Scoop. Everything I teach you could be on the test. Of course it could be. The test isn't written yet. Alrighty, last example. Holy smokes. Don't write large. Space is at a serious premium for this question. For next year's notes, I've already taken space away from this question because I didn't use any of this to give it to this question. So we're going to have to write smushed for this one, okay? X to the third plus x squared minus 4x minus 4. And on the bottom, 2x squared minus 4x minus 6. I should have made this question a little bit better and made this negative 2x squared plus 4x plus 6, but I didn't want to make you change it because it's going to end up having a very similar in behavior asymptote and a very similar shape to the last graphing question we did. But that's coincidental, and it's because I was trying to keep the numbers manageable and small for us so we didn't have to use calculators. Okay? So I want you to know that it's just coincidental. It's not some kind of pattern that you can always trust in. What we have here is a rational function whose degree in the numerator is larger than the degree in the denominator. That means it is top-heavy. And when we have a top-heavy rational function, in order to find the in-behavior asymptote, you are going to have to do polynomial long division. The good news is you can ignore the remainder because it will always tend towards 0 like this one did, and you would just cross it out. So if that's the case, why bother even finding it? I'm going to do the long division right here because, again, I've said I'm trying to save space. Let's make sure we're not missing any terms. X to the 3, 2, 1, none. We're not missing any terms. color did I do that in last time? Oh, I did the long division in black, huh? Okay. If they're the same degree, then if they have the same degree, then it's like we did here. Then it's just leading coefficient over leading coefficient. Because if you were to do the long division, what would you have to multiply this x squared by to get into 2x squared? 2. You could do the long division, but it's a waste of your time. When you could just do that. Boop. Okay? The long division always works. The long division always works. It's just not always necessary. It's necessary when it's top heavy. Okay. We are trying to make a 2x squared become an x to the third. So I have to make sure the 2 goes away. What am I going to multiply by so the 2 disappears? 1/2. And I need to make the x squared become an x to the third, x. So once again, I'm multiplying by 1/2 x. That's coincidental. It's because I didn't want us to have to deal with big numbers. I mean, I could have made it a third. I could have made it a fourth. I just didn't want it to deal with weird slopes because 1/2 slopes are easy to deal with. Okay. So anyway, it's a 1/2 x. And you'll distribute the 1/2 x. Luckily, all of these numbers are even, so they all cut in half pretty. Half of 2 is 1. X times x is x squared, or x to the third, excuse me. X times x squared is x to the third. So I have a 1x to the third. Half of -4 is -2. X times x is x squared. Half of -6 is -3, and there's an x. You are subtracting straight down. Remember, please, that minus negative means plus. 1 minus 1 is 0. 1 minus -2, that's 1 plus 2. That's 3. -4 minus -3, that's -4 plus 3. That's -1. And you could drop the -4 down. So a little bit more difficult. If you were trying to make a 2 become a 1, you said multiply it by 1/2, right? And if it was a 1, how would you make it become a 3? Multiply by 3. So just do both things. You want the 2 to become a 3. So you cut it in half and then triple it. Right? So that's plus 3/2. You cut it in half so it becomes a 1, and then you triple it so it becomes a 3. So you're multiplying by 3/2. Now, when I go to do that, I'm going to get, just to prove the point, let's see, 3 times 2 divided by 2, so that's 3, x squared. 3 times -4 is -12, divided by 2 is -6. There's an x, of course. And -6 times 3 is -18, divided by 2 is -9. Now, if I were to go through the subtraction, there would be a remainder that starts with x, right? Looks like it would be a remainder of 5x and change. But 5x and change over a quadratic is bottom heavy. And that bottom heavy thing always goes to 0. So the remainder isn't necessary to find. Because that remainder will head towards 0. Every time. So my in-behavior asymptote is this linear equation. Y equals 1/2 x plus 3/2. Let's go ahead and graph that. Oof, man, that y-intercept, 3 over 2. That's 1.5, right? So 1.5 is right about here. Now here's the thing. Could I go up 1, right 2 from that? Sure, but I'm going to be guessing a whole lot of 0.5s on my picture, aren't I? Because every time I go up 1, I'm still at 0.5s, aren't I? And that kind of bites, right? because it's going to mess us up a little bit. So a trick that I figured out a long time ago is when your slope and your y-intercept have the same denominator, then all you have to do is go a little bit left or right, and you'll find whole pretty values. For example, if you plug in x equals 1, you get 1/2 plus 3/2, right? 1/2 plus 3/2 is 4/2, which is 2. So this thing has a point at 1, 2. And now you could follow the slope of up 1, right 2 over and over and over again, and you don't ever have to worry about guessing where the 0.5 is anymore. And you can also go down 1, right 2 from this point. Or down 1, left 2, excuse me. Down 1, left 2 puts you right here. Because graphing decimals bites. But graphing whole numbers is easy. And that trick works every time the denominators are the same. You just go a little bit to the left or go a little bit to the right, and you will find pretty points. And again, I'm going to turn the paper sideways so I can connect my dots. So is the in-behavior asymptote always going to be something with a slope of 1/2? No, it's not. That was just for note-taking purposes. It's coincidental. It's because I wasn't worried about making sure the slope was different, because the skill here is using the polynomial long division to find the in-behavior asymptote. But to find the other asymptotes, I am going to have to factor. And how do we factor something like this? Grouping will work. You hope grouping works so you don't have to do the P over Q stuff. So grouping. Again, space is at a premium. So now that we've done our long division, now you know what? I'll just rewrite it. I've saved a little bit of space already from period 1. Grouping. Time to artificially group some stuff. Like that. In the first orange group, what's the GCF? X squared. And in the second orange group, what's the GCF? -4. And in both of them, what's going to be left inside is an x plus 1. In the denominator, start with the fact that it has a GCF of 2. The top, I have an x plus 1 and an x squared minus 4. That's a special case, and that's going to factor. In the denominator, though, I'm looking for the two numbers that multiply to a -3 and add to a -2. Well, that's 1 and -3. Lastly, the x squared minus 4 factors. Oh, wait a minute. The x plus 1's cancel. That just put a hole in my graph. I'm going to have a deleted point at the x value that makes that equal 0. And removable discontinuity. But I can factor this. It gets me x plus 2, x minus 2, because it is a difference of 2 squares. And in the bottom, I have a 2 and an x minus 3 still. Let's track down that deleted point since we've already done this. So we know we have a hole at x equals -1. And we need to know the y value for the hole in the graph. And the way you do that is you substitute in x equals -1 into the simplified version of the function. Yep, the factored and simplified. So we've got -1 plus 2, which is just 1. -1 minus 2, -3. So right now the top is -3. On the bottom, 2 and 2 times -4 is -8. Oops. So they're both negative. That gives me positive 3 over 8. Oh, well, that was supposed to be red, not orange. You probably can't see the difference, but I can. So our graph has a hole in it at -1, 3/8, right? It doesn't exist there. It wanted to, but it doesn't. Might as well go there, -1, 3 over 8, and put an open dot. And if you make it fat enough, no one's going to be able to argue with you until you put it in the wrong spot. Also, if you look at this, you can see where your vertical asymptote is. You're not allowed to divide by 0. So x equals 3 is a vertical asymptote. And just like before, I need to know coordinates it actually does go through. I know it wants to go through that coordinate, so I already know I'm down here. We already know that. But we might as well find the x-intercept and the y-intercept. For the x-intercept, no, y-intercept, that one's easier. For the y-intercept, you're always using x equals 0 because the x always equals 0 on the y-axis. And for that one, I always go back to the original and I go, if I covered up everything with an x, what would I have left? Looks like -4 over -6 to me. Positive 2/3. And for the x-intercepts, and I have to put an s on the end of it because there are two numbers that make the top equal 0. Those two numbers are +2 and -2. So plus or minus 2. Just like that. Now, like I said, we already knew the shape, but we wanted some actual coordinates. There we go. Lastly, to the right of that red dotted line, we need to know if we're above or below the green dotted line. Now, you probably have a sneaking suspicion that it's up there, and you'd be right. But there's no way for you to be certain of that without lots and lots and lots of practice, without testing a coordinate. So we're going to test a coordinate just to be absolutely certain that that's how that works out. So I like to plug in a number that is close to the x value, there we go, where your vertical asymptote is, because I don't want the numbers in my fraction to get huge. So stick close to the asymptote. I'm going to go with x equals 4. So I'm going to plug in x equals 4, and I'm going to do it here because it's already factored. And to get y equals 4 plus 2, that's going to be 6. 4 minus 2, that's 2. So I have 6 times 2 on top. And on the bottom, 2 times 4 minus 3. Well, that one's easy. So I've got 6 times 2 over 2, which is 6. Because the 2's just cancel. 4 minus 3 is 1, so I don't have to worry about it. So I have a coordinate at 4, 6. That is way up here. Get close to the 2 lines. And that is it. It's a big question. I'm aware. It's got a lot of skills. Yes, it does. Are there any questions I can answer for you, though, to help clear anything up at all? What ifs? Why didn't you use? Couldn't we haves? Anything like that? No? No? All right. Wow, you were really small. All right, well, I appreciate you, nerds. I hope it all made sense then.